afternoon to our audience and our esteemed judges. This year's theme for topic is about a mission. A mission to where, you ask? A mission to Mars. But why Mars? Why not any other planet? I mean, there are 7 other planets. Well, you see, Mars is actually pretty similar to Earth. That is the surface area of Earth's dry land. It has an average temperature of 62 degrees Celsius and wide variation due to the thin atmosphere. Speaking of the thin atmosphere, it's 100 times less dense than the Earth's and primarily composed of carbon dioxide. Because of this, it lacks an ozone layer, which means subsequently significantly more UV radiation compared to Earth. Human exploration in Mars is a fascinating history, but I think the main point is in 2012, when NASA landed a sky crane that hovered over the surface of Mars and lowered the Curiosity rover down. This proved we could land massive high-tech laboratories on Mars. Currently, SpaceX and NASA are racing towards the first missions that can carry 100 plus tons of gear. There are numerous challenges for Martian exploration, but I think the main challenge is Martian radiation, which is why my experiment based around radiation protection frameworks for long-duration human occupancy on the Martian surface. I'll call it radiation shielding on Mars. But why is this so important? You see, Mars requires shielded habitats to protect astronauts from DNA-damaging space radiation, which can cause damage to human cells. This experiment simulates real-world challenges of Martian radiation protection by using UV-sensitive beads to visually test which material best shield astronauts from harmful exposure. Let's talk about my experiment. My research question is which material provides the most effective radiation shielding for sustainable human habitat on Mars? My hypothesis is highly enriched materials such as clay will reduce radiation exposure the most. The method is to mix silica sand with red iron oxide to make a simple simulated Martian regolith. Then test UV UV protection by covering UV sensitive beads with different materials and then recording bead color changes over time. Now, before we go any further, I would like to ask the judges to start over here. So basically what you're going to see is there are 3 types of beads over here. 2 of the beads are shielded, and 1 of the beads will actually be shielded by my homemade regolith. So you guys can do a little bit of a competition. Thank you so much. So you guys can choose which beads. So you guys can be a pair over here. You guys can deliberate and choose which beads. Okay. And this, please choose me. Regolith shielded. And this, sir, this leaves this bead for you. 1 bead. Actually, yeah. So I just want to remember that you are having the wording. Yeah. You guys are having the word for me, and you will have the regolith bead. So I will now place them. Please continue here. First, I'll place the water bead here, and the regolith bead I'll bury it under the soil. And the aluminum foil bead will be placed over here. Then shine my UV flashlight on it, capturing all of them. Right, that should Now I'll just continue my presentation, and in the conclusion, we'll figure out which bead is the best protector. So let's start with my 3 phases. Start with phase 1, creating the simulated Martian regolith. For this, I need red iron oxide plus my silica sand. So, how did I make my simulated Martian regolith? Well, first, I measured my silica sand and my red iron oxide to obtain 1,350 grams of my Martian regolith. I then combined them in a clear plastic box, and I shook and stirred it until the entire sand was completely and evenly coated in red. And this was the final result. That's what you see there. Next is building the habitat and controls. So this is just going to set up how my experiment will be. I shine UV flashlight on the bead for 1 minute. The dark greenish the bead is, the more dark green the bead is, means more radiation has been absorbed. We don't want that. The lighter the bead is, the less radiation has been absorbed, and the material actually works. We want that. As you can see, this bead is the control bead. There was no shield on it, so it's very dark. I've also made a table. So on the x-axis is the types of beads. On the y-axis, it's a scale from 1 to 5, from light to dark bead. The control bead is in the highest scale, 5. Next is phase 3, testing shielding materials. For this, I needed water, plastic wrap, aluminum foil, white paper clay, and my Martian regolith. So let's start with the regolith bead. So you guys are going to get the answers quickly enough, but yeah. So I buried the bead under my marshmallow gullet and then I showed UV flash on it for 1 minute. After I took it out, as you can see, there's only a little bit of green spots on them, but usually a red tint. So on the table, I kept it in the 1 to 2 area. Next we have the water bead. So same as the one you just see. So I shone a UV flash on it for 1 minute, just like the others. Now I thought that this would be a good shielder since it has hydrogen. And scientists think that hydrogen is actually a good shield, but it turns out it isn't really that much. As you can see, it's pretty green. So on the scale, I kept it in the 2 to 3 range. Next we have the plastic bead, which I wrapped in plastic wrap, and then I shone a UV flash on it for 1 minute. So same process as all the others, except this bead was a little bit higher in the water and a slightly greenish hue. Next is the aluminum foil bead. So fun fact about aluminum is actually the material that engineers and space scientists use in real spacecraft because aluminum is known for reflecting radiation. So I had high hopes for this one. So after I shone a UV flash on it for 1 minute, I unwrapped it, and as you can see, there's only a little bit of green over there, not that much, only on the couple, just a little bit on the sides. So I kept it more over 2 to 1, but higher than the marshmallow. Next is the clay bead. So I molded the clay over the bead for around, I let it to dry for an hour, and I shone a UV flash on it for 1 minute. After time was up, I soaked it for about 15 to 20 seconds, and then as you can see, there's absolutely no green tint on them. Just a little bit of clay residue. So I kept it on the ice. Now looking at this graph, you can see that the top 3 contenders are the regalia bead, the foil bead, and the clay bead. So I did the logical thing and combined it to make a storm shelter. So how does the storm shelter work? Well, it has a clay base with an aluminum foil wrapping, and my marshmallow on the top, with not 1 but 4 beads in the middle. So this is the moment that every experiment has been leading for. So I placed my beads in the aluminum and then covered it with my clay and aluminum and shone my UV flash on it. I shone UV flash on it for not 1 but actually 10 minutes. I really want to test this to limits. Once I wrapped the aluminum, as you can see, there's absolutely no radiation on it, which means that the storm shelter had a success rate of 100% and protected it from the UV rays completely. So my conclusion is that clay is the best material that can be used to protect against Martian radiation. Martian regolith is also a good shield, but there are certain health issues since there are toxic chemicals called perchlorates. So now before I continue, I think it's done shining the way that I want it. As you can see over here, the water bead is really green. As you can see, that means it's darker. And this one is just a red tint. It's really not that green. Only a little bit inside. And aluminum one, we'll have to unwrap it. As you can see, I mean, it's got a little tint, but not really that much. So yeah.
I'm sure you would like to see it also. Maybe you can get someone to pass the ball around.
So also just simulates my storm shelter in AI, and this is just how the image looks. So I also did an evaluation. So after finding out that clay, aluminum, and regolith had the best results, I wanted to know why. So I came up with 3 hypotheses for each of them. So for clay, I think it's because clay has a dense structural matrix that provides a solid physical barrier that easily absorbs and stops these large, slow-moving alpha particles from the UV rays. Evaluation 2. So aluminum was actually a really good shield because when UV photons strike the aluminum surface, they drive the collective oscillation of the delocalized or free electrons, which efficiently reflects the radiation and prevents it from passing through. For evaluation 3, I think regolith is a good shield because this is primarily due to the scattering effect and density packed granular molecules, and also because iron oxide is a strong absorber of ultraviolet radiation. What are the strengths of my experiment? Well, you see, it's a control covariate framework, which means everything was tied back to the control bead, all reflected from the control bead and compared based on the control bead. Another thing was it was a progressive experimental design, eventually culminating into the storm shelter. So with structures and logical steps. First creating the Martian regolith, then testing the materials, and finally making the storm shelter based on my 3 best materials. What are the limitations? Well, you see, UV light does not fully replicate the full Martian radiation environment. Space on Mars is littered with not only UV rays, they're littered with SEPs and GCRs, solar particle events and galactic cosmic rays, which behave fundamentally different from UV photons and way more stronger. Number 2, there is no repeated trials, and my experiment was also a quantitative experiment instead of qualitative experiment, which is obviously based on opinions. What are the future goals? The future goals of every space scientist is to land a rocket on Mars and create a civilization there. But my future goals for my experiment is to build a better and more professional and scientifically accurate shelter that will be put to test on a more accurate Martian terrain. And I already took a step to this. This is an example base I created. It might not be the best base, but I would always like to continue improving this. I also would like to work with researchers from Tokyo University who found out that regolith on Mars soaks up water. Now, I want to figure out if this is a new way to create a shield material. I'd like to thank you to the paper, Fabrication Testing Path Components Using In-Situ Materials for Martian Exploration by these authors. I'd also like to thank the effectiveness of Martian regolith as a radiation shield by these authors. Also, thanks to NASA for the data obtained from the website. Ladies and gentlemen, sorry for the delay. Thank you.